Sound is a fascinating phenomenon. It's the result of vibrations, and those vibrations travel through the air as waves. But how does it all work? Well, let's journey into the realm of sound and its physics. Imagine you're sitting in a quiet room, and suddenly your phone rings. That sound you hear? It's created by vibrations. When your phone rings, it sets off tiny vibrations in the air around it. These vibrations create waves of pressure that ripple outwards, much like the ripples you see when you drop a pebble into a pond. These waves of pressure, or sound waves, spread out in all directions. They're invisible to the naked eye, but they're constantly moving through the air, carrying the sound of the ringing phone to your ears. But what makes the sound of a ringing phone different from, say, the sound of a barking dog or a playing piano? This is where the concepts of frequency and amplitude come into play. Frequency refers to how often the waves occur. High-frequency sounds have waves that are close together, resulting in a high-pitched sound like a bird's chirp. Low-frequency sounds, on the other hand, have waves that are further apart, resulting in a low-pitched sound like a drum beat. Amplitude, on the other hand, refers to the size of the waves. Larger waves create louder sounds, while smaller waves create softer sounds. So a loud ringtone will create larger sound waves than a quiet one. So, from the gentle hum of your refrigerator to the roaring engine of a jet plane, each sound we hear is the result of complex physics at work. Vibrations create sound waves, and the frequency and amplitude of these waves shape the sounds that reach our ears. As we delve deeper into the world of sound, we begin to appreciate the complex physics that create the symphony of sounds we hear every day. Our ears are marvels of biological engineering. They allow us to perceive and interpret these sound waves. But how, you might ask? Well, let's immerse ourselves in this auditory journey. The outer ear, known as the pinna, is our first point of contact with sound. Its unique shape helps us capture sound waves from our surroundings. Once captured, these sound waves travel down the ear canal and strike the eardrum, causing it to vibrate. Now, these vibrations aren't just random movements. They carry with them the essence of the sound, whether it's the soft whisper of a lover or the thunderous applause of a crowd. And it's these vibrations that kickstart the next phase of our auditory journey. Deep within our ear lies a tiny, spiral-shaped organ known as the cochlea. Once the eardrum vibrations reach the cochlea, they are transformed into electrical signals. But the magic doesn't stop there. These electrical signals then embark on a journey to the brain via the auditory nerve. Once in the brain, these signals are deciphered and recognized as distinct sounds. This is where the perception of pitch, volume, and directionality comes into play. A high-frequency signal is perceived as a high-pitched sound, while a low-frequency signal is perceived as a low-pitched sound. Similarly, a high-amplitude signal is perceived as a loud sound, and a low-amplitude signal is perceived as a soft sound. Directionality, on the other hand, is determined by the slight differences in the time it takes for sound to reach each ear. Our brain uses these minute differences to triangulate the source of the sound, helping us identify where it's coming from. So the next time you hear the melodious notes of a song or the comforting rhythm of a familiar voice, remember the intricate journey that sound undertakes. From the outer ear to the depths of our brain, each step is a testament to the marvels of nature's design. Our ears and brains work together in harmony, transforming vibrations into the sounds that shape our perception of the world. Scene script. Have you ever wondered why your knuckles crack when you flex your fingers? It turns out there's some surprising science behind it. So let's jump right in. When you crack your knuckles, what you're hearing is not the sound of bones grinding together as some might think. Instead, the sound is all about bubbles. Yes, you heard that right, bubbles. Here's how it works. The synovial fluid that lubricates your joints contains dissolved gases like oxygen and nitrogen. When you stretch or bend your joint, you increase the volume of space in which the synovial fluid resides. This sudden increase in volume lowers the pressure, causing the dissolved gases to come out of solution and form bubbles. This process is known as cavitation. Now, the formation of these bubbles alone doesn't cause the cracking sound. The real kicker is when these bubbles collapse. That's where the distinctive pop comes in. When these gas bubbles collapse, they create a rapid pressure change within the joint, and voila, you have the satisfying, or for some, cringe-inducing sound of knuckles cracking. Now you might be wondering, is cracking your knuckles bad for you? Well, that's a topic of ongoing debate among scientists and health professionals. Some studies suggest that habitual knuckle cracking may lead to hand swelling and decreased grip strength. Others find no significant harmful effects. A study published in the Journal of the American Board of Family Medicine found no increased risk of arthritis among habitual knuckle crackers. But before you start cracking away, remember, just because it's not harmful doesn't mean it's beneficial. So the next time you crack your knuckles, remember, you're not just annoying your desk neighbor, you're demonstrating a fascinating physical phenomenon. Whether you find the sound of cracking knuckles satisfying or irritating, there's no denying the fascinating science behind it. Now, let's talk about something we all know, the soothing sound of rain. But did you know that the size of raindrops can affect the sound they make? It's true, and it's all thanks to the fascinating world of acoustics. Picture this, a droplet of water, suspended in the air, falling towards the earth. As it descends, it collides with the surface below. This collision generates a sound wave, a tiny echo of the raindrop's journey. But not all raindrops are created equal. Some are small, like a pinprick, while others are larger, more akin to a marble. The size of the raindrop influences the sound it makes when it hits a surface. Larger drops create a lower-pitched, more resonant sound, while smaller drops produce a higher-pitched, more delicate sound. This is because larger drops displace more air as they fall and hit the ground with more force, causing a more intense vibration and hence a lower-pitched sound. On the other hand, smaller drops displace less air and hit the ground with less force, leading to a less intense vibration and a higher-pitched sound. But there's more to it than just size. The type of surface the raindrop hits also plays a role. Different materials absorb and reflect sound waves differently. A raindrop hitting a leaf, for instance, will sound different from a raindrop hitting a tin roof or a puddle of water. The texture of the surface, its temperature, even its moisture content, all these factors can subtly alter the sound of a falling raindrop. So, in essence, each rain shower is a unique symphony, with every raindrop playing a different note. So next time you're listening to the soothing sound of rain, remember, there's a symphony of science playing out in every drop. As we've discovered today, the sounds around us are more than just noise. They're a testament to the complex and fascinating world of physics and biology. From the gentle hum of a refrigerator to the soothing patter of rain against a window, each sound is a small symphony of science, playing out in real time. We've journeyed through the physics of sound, understanding how vibrations become the symphony of noises that color our world. We've seen how frequency and amplitude shape the sounds we hear, and how our everyday objects create these auditory waves. We've explored the marvel of our ears, the intricate biological machinery that allows us to perceive and interpret these sound waves. We've delved into how our brain interprets pitch, volume, and directionality of sounds, adding depth and dimension to our auditory world. We've cracked the mystery of knuckle cracking, learning about the formation of gas bubbles and the distinctive sound they produce. We've also touched upon the ongoing debate about whether it's harmful or harmless, a question that continues to intrigue scientists. Lastly, we've listened to the soothing sound of rain, understanding that the size of raindrops can affect the sound they make. A symphony of nature, each droplet is its own instrument playing a part in the grand orchestra of life. In essence, each sound tells a story, a narrative of the physical world interacting with biology. These are more than mere noises. They are the whispers of the universe, the echoes of scientific principles at work. So the next time you hear the whirring of a fan, the rustling of leaves, or the crackle of a fire, pause for a moment. Listen closely. There's a world of science waiting to be discovered in every sound. Thanks for joining us on this auditory adventure. Stay curious, keep exploring, and we'll see you next time on Investigating the Universe.